Hello everyone. In this video, we will learn a trick called considering different cases that together with the fundamental counting principle we will be able to use in this counting problems. Well, the situation is that sometimes you cannot apply fundamental counting principles. So sometimes to apply let me write fundamental counting principle, we need to separate different or define different cases, define or consider different, I will write disjoint cases, meaning that they won't have any overlap. So I would like to say that we will form a trees like that. Then on each branch you can use fundamental counting principle. So that is basically your art of counting, how to separate these things. And what you do, well, basically you multiply cases, yes? So R1 times S1 times T1. Here you do R2 times S2 times T2, and then R3 times, and so on, yes? But when you're trying to find the total number, that's basically NU, what you need to do, this is what we did in the counting trees. You have to add these guys here. Okay. So you first do fundamental counting principle for each branch and then add all those cases. Okay, let's see this in some examples and you'll notice that it's a very natural way of doing this. Okay. We are going to use digits of 2019. We had as an example before. So the digits we are allowed to use are these guys. But we are only allowed to find, first of all, for part one, not allowed any repetition. And the number we are getting must be less than 29 hundredths. Okay, so we start, just you see the question, you right away go into that. So I want to have the first, then second, how many ways we can do second digit, the third digit, and the fourth digit, yes? So for the first one, I can use either 1 or 2. I cannot use 0 because you see the numbers cannot start with 0. And I cannot use 9 because if I start with 9, then will be a number bigger than 29. So there will be only 2 possibilities here. Then let's say I started with 1. Any number after that, I can put either 0 or 2 or 9. So there will be 3 possibilities here, including 9. So there will be 3 possibilities. But if you start, so let me write like that. But if you start with 2, then in the second digit, we cannot use 9. Because if you use 9, there is a 1 somewhere appearing. That will be a number bigger than 29 hundredths. So there will be only 2 possibilities. And what that breaks that ease that we usually have in fundamental counting problems. So you have to now consider 2 cases. The number starts with 1. And the number starts with 2. The first thing you have to notice that the cases that I'm including there, they don't have any intersection. They are disjoint basically, yes? Now, if I start with 1, so that means that for the first digit, the choice is there, yes? So there's only one possibility is there. So I already choose 1 for the first one, and that's there. For the second digit, we can either use 0, we can use 9, we can use 2. All cases would give us a number less than 2900s. We are not allowed to use 1 itself because the repetition is not allowed. So there will be 3 possibilities there. Now, for the third one, okay, I have used 2 of these digits. There will be 2 remaining, and then there will be 1 left for the last one. So the all numbers that we can create starting with 1 will be only 6, yes? How about starting with 2? Okay, so if I start with 2, first digit, second digit, third digit, fourth digit. If I start with the first, starting with 2, it means that the first one we have chosen, it's fixed. Remember, I'm including the number of possibilities for each digit, yes? So for the first one, I can use 2. For the first one, I have decided I can use only 2. For the second one, now, I cannot use 9 and I cannot use 2. Why? Because if I use 9, then the digit after that will come 1 and it will be a number bigger than 2900s. So that makes the second digit, the possible ways we do the second digit 2. Why? Because, well, either you can use 0 or can use 1. Okay. How about the third digit? For the third digit, now I'm allowed to use 9, and I have already used 2 of the digits, other digits. So there will be 1 left from those ones, and the 9 you added, there will be 2 there, and then that is 1. So you multiply. There are 4 numbers that you can make starting by 2. But how we find the total number? Okay, this is a counting tree, yes? Here is 6, here is 4. We are looking for NU, and that is 4 plus 6. There are 10 numbers that can satisfy the first condition. Okay. The second condition asks the same thing. We are only interested in the cases that there are 200, they're less than or equal to 2900, but the repetition this time is allowed. So that is the difference. Okay, so we will go this time again. This is part 2. So depending, starting with 2 or 1, okay? So I will start with with 1 and starting with 2. Okay, let me write okay, nice. Starting with 1, we will go like that. Number of possibilities for the first digit, the number of possibilities for the second digit, third, and fourth, yes. Since there is no condition that we need to be worried about, for the first one, I will use just 1. The number 1, there's only 1 possibility there. For the second one, now I can use any of the 4 digits possible there, available there. Because the repetition is allowed, I can use 1 again. So there will be 4 possibilities there. For the third one, there is the 4 possibilities, and none of these will generate a number bigger than 2900. Actually, the most we can get is 1999. Okay, and that you see that now repetition allowed changes the story. There will be 64 possible cases there. Now let's go down and consider the cases that starts with 2. If we have a number starts with 2, let's just write down a few cases here. I will erase that. So it starts with 2. Then I can put what numbers after that? I can put, if I put, for example, 1, then these two, we are allowed to use any number we want. But if I have the second digit to be 9, the only thing that I'm allowed to use are 0, 0. And you see that this will happen also if you do 2 here or if you do 0 here. And that tells me that there is also another branching here. The second digit is 9, or the second digit is not 9. Okay, let's see now how this works. So if that's the case, so let me set up the number of cases for the first digit, the number of cases for the second, number of cases for the third, and number of cases for the fourth. Yeah. So we have decided the first one to be 2, so there's only one possibility there. For the second one, we have decided it's 9, so there's only one possibility there. So I have 2, 9. If I use that, the next digit must be 0. So there is only one possibility to do that one there, and one possibility. If you use any other digit, you use 2, 1, anything other than 0, it will give you a number bigger than 2900. So the number of possibilities this way will be 1. However, if you do use something which is not 9, so this will be the number of first, the number of second, the number of third, the number of fourth. So we have already decided for the first digit, it's 2. For the second digit, we don't want to use 9, but all other 3 digits are available. Remember that we are allowed to use repetition here. So there will be 3 possibilities. I can use either 2 or 1 or 0. Then for the third digit, now I can use even 9 itself, because the numbers, the digits that we have, it would generate 2100 something or 2200 something or 2000 and something in tens and units. Okay, so that means that in the third one I can use all 4 digits, and for the fourth one I can use all 4 digits. Okay, so you have now the numbers there. You multiply fundamental theorem of fundamental counting principle. Here is 16 times 3 is 48. Remember, we are interested in NU in this tree, so that the total number. So you apply the counting tree properties. There is one there, there's 48 there. Sums of the outgoings must be equal to the incoming branch. So this will be 49, which is 1 plus 48. And there is 64 there, so I just write that one there. What will be the total? Total will be 64 plus 49, which will be 3 there, and then 113. So there are 113 numbers if the repetition is allowed, and we cannot have a number bigger than 2900. hundreds. You see that the changing conditions changes everything. So I separated not only once, twice into different cases and used the tree structure and counted everything down. Okay, let's do one more example before we finish this video. In how many ways can Hannah arrange 9 books on a bookshelf using 7 math books and 5 physics books? Obviously, some of these were left out at the end because there are in total 12 books, but we have 9 books. A shelf can get only 9 books. If she would like to, the subject of the books alternate, means that if a book is physics, the next one math, then after that must be physics and so on. Why here it matters? Okay, so I can start then the first place, the second place, the third, fourth, let me just write once, and fifth, sixth, seventh, eighth, and ninth. Yes. So the point is that, okay, to start with, am I going to put math book or physics book? Because it's important. It's going to change the game. If I start with the physics, I have 5 possibilities for the first part. But if I start with math, I only have 7 possibilities available. That's where the cases come in. So I can copy this. So I will separate this one into 2 cases. One starting with math book, and the other one starting with physics. Yes, and that's the 2 different cases that you can have. Paste. Okay. Oops. Sorry. Okay. So how does that changes the story? Well, okay, so here, the first one, the math. If I start with the math, there will be 5 for the first one. Then the second one needs to be physics. Then there will be 7 there. And the third one will be 4 because it's math and one of the books we already used it in the first place. Then the next one needs to be physics. Then we have used one of them already. This is 6 will give me. And then there will be 4. Okay, this will be, you see, these are the math ones. Yes. Then the next math will be in the 7th place. There will be 2 there. And then the next math will be in the 9th place. There's only 1 possibilities. And for the physics, I started with the 7, go to there, and then now in the 6th place I can put only 5 of physics possible available, and then the 8th one we have 4 of them. So I'm doing that. Okay, that's nice. Now you're doing the fundamental counting principle. You have to multiply all those guys. Well, this is a big number. I'm not going to compute that. So I will just write 5 times 7 times 4 times 6 times 3 times 5 times 2 and times 4 and times 1. Okay, just write that. And then for the case that we start with physics, now we will have the 7 for the first part, then for the third one, which is going to be physics again, there will be 6, then there will be 5 at the 5th one, there will be 3 on the 7th one, and there will be 2 in the last one. These are physics books, yes. Now for the math books, I will start with the 2nd place. There are 5 possibilities. Then there will be 4, which will be in the 4th place. Then there will be 3 possibilities for the 6th place, and there will be 2 possibilities for the 8th place. And as you can see, this is going to give me a little bit different number. 4 times 5 times 3 times 3, and then times, this is strange, I missed something here. Yes, I can see now. This must be 4, then 3. Oh, this is much better. Yes, 7, 6, 5, 4, and 3. And then after that will be, this will be 4. And then this will be 2. And then that will be 3. And this is a huge number. But the point is that neither of those ones are the correct numbers. You have to add these two numbers. And that is the total number of the cases that Hannah can arrange those books on the shelf, alternating the subject. Okay, so these were examples that we separated in different cases and used the tree structure and find the total number. Okay.